Welcome back. We're going to finish up skeletal muscle talking about tension formation and some of the characteristics of how muscle forms tension, and then also talking about the metabolism. What is the source of the ATP that we know muscle needs to be able to contract? So we're going to first talk about tension. And the simplest way to think about it is if you have a single action potential coming from that somatic motor neuron traveling along the plasma membrane of the skeletal muscle cell, what's going to happen in terms of how much contraction or how much force is formed? And that's what's shown on the left-hand part of this diagram, where if we have a single action potential, the resulting contraction is going to be called a twitch. So twitch is going to be the result of a single action potential. And because of that action potential, we'll have an increase, a very rapid increase in the amount of calcium in the cytosol, almost a maximal increase. However, the ATPase in the sarcoplasmic reticulum will start to remove calcium very rapidly. So although we have this huge increase in calcium, it's also going to decrease in concentration in the cytosol very quickly as well. And as you can imagine, it takes time for the calcium to diffuse into the myofibril and to bind troponin, cause tropomyosin to come off the actin to allow for the myosin to go through its cycle. And so because of this pretty quick decrease in calcium, we, with a twitch, do not have maximal tension generated. So we have tension, but it's not maximal with a single action potential. So it increases the tension that it's forming, the amount of force it's generating through the contraction, but then it's also going to relax fairly quickly. However, notice, and this is going to be a very important difference between skeletal muscle and cardiac muscle. In skeletal muscle, we have an action potential extremely similar to those in neurons that are very short. Even when you consider the inactivation, the refractory period of the sodium voltage-gated channels, the action potential in skeletal muscle is very rapid, about 5 milliseconds. Whereas with our twitch, it's going to be about 100 milliseconds. And so what that means is if we have action potentials more frequently, and we said with a twitch we're not forming maximal force, not even close, that if we have more frequent action potentials, then we can increase the tension because it becomes additive. Then that's keeping the calcium levels in the cytosol high and giving enough time for everything to diffuse and for tropomyosin to be removed so that we can actually get many of the myosin heads cycling and shortening the muscle cell. And then we can continue to have very frequent action potentials as we do in the right-hand side of this graph so that we reach what we call tetanus, which is maximal contraction that is somewhat sustained. And so this can be accomplished in skeletal muscle because the action potential duration is so short in relation to the twitch duration, and this is going to be a big difference between skeletal muscle and cardiac muscle, and Dr. Jacoy will be telling you more about that very soon. We can also talk about the velocity of shortening, where we're looking on this graph at the amount of load. So how large is the load, which is basically like saying how heavy is the load, and then looking at the velocity of muscle shortening or lengthening, where it makes sense when we have zero load, when you're just contracting the muscle, as I am right now, then that's when we're going to have the maximum velocity of shortening. So that would be this point here. As we increase the load, then the velocity of shortening will get less and less. So it will take longer to shorten the muscle. But when we're doing this sort of contraction, we are making the tension that the muscle is producing greater than the load, and so we're getting shortening of the muscle, and this is called isotonic shortening. Isotonic meaning keeping the same tone, the same amount of tension, and since it's greater than the load, then the muscle is shortening. So we're able to do that with these small loads because we can easily form more tension than the load. However, as we keep lifting heavier and heavier things, that's when the velocity greatly reduces. However, we're still able to shorten our muscles and produce more force than the load so that we have shortening. But eventually, as we keep piling on weight and piling on weight, we will eventually get to this point right here, which is going to be where we have isometric contraction, which is where we have reached our maximal load that we can hold. So it's just heavy enough that we can no longer shorten our muscles, but yet we can hold it. So this would be an isometric contraction, meaning that we're making the tension equal the load, and the muscle is not getting shorter. It's staying the same length. So this would be an isometric contraction when you can't produce any more force, but you're able to still hold it up. If you add even more weight, that's when your arms are just going to start to fall, because now the load is greater than the tension that you can form. And so what you're going to have is a lengthening contraction where you're still contracting your muscles, but they're getting longer. The interesting thing to think about is how we use these different states of muscle just in everyday life. So, for instance, if I want to pick up the stylus, then I'm going to make the tension in my muscle greater than the load, and so the muscle will shorten. If I want to just hold this in the air, I will make the tension in my muscle equal to the load of the stylus, and that will be an isometric contraction, and I'll be able to just hold it. So by setting the tension, we can accomplish these different tasks. Now, if I want to put this down slowly, instead of just dropping my arm and completely relaxing this muscle, then what I will do is make the tension less than the load, which means that the muscle will get longer, and I will be able to gently put this down. So we use these different states in everyday life. Another example of a lengthening contraction happens in your quadriceps when you go to sit down. So when you sit down, you don't just relax all your muscles and slam into the chair. You ease yourself into the chair, and you're contracting your quadricep muscles, but they are lengthening to be able to lower you into your seat. And so you make the tension less than the load of your body so that the muscle gets longer, but that you ease yourself into your chair. The amount of tension that is formed is also going to be based on what's happening at the microscopic level of the sarcomere. Let's take an extreme example of if your muscle is overly stretched, as shown here all the way on the right in this graph, where you can see that the heads of the myosin at the end of the thick filament, most of them are not able to contact the actin anymore because the sarcomere is so stretched. And as a result, as you can see on this graph, that means that the percent of maximum force that can be formed when the sarcomeres are in this state is low. Similarly, if the sarcomeres are too almost compressed or too shortened, where the myosin is already bumping up against the Z line, so it really has no more space to crawl, and it can't shorten the sarcomere anymore, then again, the amount of percent of maximum force that can be formed when the sarcomere is in this state is also reduced. So it makes sense that the sarcomere needs to be stretched enough that there's still some room for contraction in order to form some force, and not overstretched so that the myosin heads can still fully contact the actin in order to contract. And so these are the states that produce the most force. And luckily, these are also the sarcomere lengths that are seen in the body. So for the vast majority of our skeletal muscles, they're going to be constrained by the skeleton, which is going to constrain the sarcomere into this sort of geometry that provides maximal force. It's only going to be in states of injury where you may see some of these other less optimal conformations of the sarcomere. We're going to switch gears to talking about metabolism. We know that we're going to need ATP in addition to calcium to be able to have the cycling of the myosin heads and to shorten the muscle cells. And so what is that source of ATP going to be? When muscles start contracting, they're going to have a certain pool of ATP that they can use, and that will only last roughly a second. So that's not going to be a significant source of ATP. The muscles can also rely on creatine phosphate, which is going to, through the actions of an enzyme, be able to convert ADP to ATP. And since this is going to be a single enzymatic step, this is going to be very rapid, very efficient. So it's able to make 4 moles of ATP per minute because it's just a single enzymatic reaction to convert ADP to ATP. The limiting factor is that there is a limit to how much creatine phosphate a muscle can store. And so in that regard, the creatine phosphate is going to last for about 8 to 10 seconds when you're doing a vigorous exercise. So the first 8 to 10 seconds of exercise, creatine phosphate will be a major contributor to the production of ATP, which means that you're going to use it primarily when you're doing something like an 100-meter dash that lasts about 10 seconds. That, however, using that creatine phosphate allows for other pathways to have time to get going, to get initiated. And so another set of pathways that will start to produce ATP while the creatine phosphate's being used is going to be anaerobic metabolism pathways, which is going to convert glucose to lactic acid, producing ATP. So the energy source, the fuel for this will be glucose as well as muscle glycogen, which is a polymer form of glucose. It produces, it's pretty efficient because you're just using one pathway, or I should say it produces a lot of ATP per minute. So it's 2.5 moles of ATP per minute versus creatine phosphate was 4. However, it's going to be a limit to how long that process can go on, and so it will last for roughly the first 1.5 minutes of vigorous exercise. After that, then the more dominant sorts of pathways are going to be aerobic metabolism, meaning that they require oxygen, and this is going to be the most efficient pathway because you're going to completely oxidize fuels, completely oxidize them to CO2 and water. So that will, if you're using carbohydrates, require doing glycolysis and then using the TCA cycle to then send NADH and FADH into oxidative phosphorylation down the electron transport chain to produce lots of ATP. So the fuels get completely combusted. And you can use not only glucose, but then you can also do fatty acid oxidation. So you can use both glucose and fatty acids, and the vast majority of us have many, many ATP molecules stored in the form of fat. So it's almost really unlimited store of energy when you use aerobic metabolism. And however, since you're doing all of these pathways, it doesn't form a lot of ATP per minute, but it certainly can last you for a long time. So if you do a marathon, you're going to be doing a lot of aerobic metabolism. We're going to talk just a few minutes now about fatigue, which is usually not going to be due to a decrease in fuel stores. Instead, it's going to be due to other changes in the ionic or in the levels of metabolites that are in the muscle cell. But you can think of the fatigue state in some way as a protection for the muscle. So fatigue is going to mean that the muscle performance is reduced because it's been used. Okay, that makes sense. We've all experienced fatigue of our muscles. However, if you think about it, if the muscle was allowed to run and continue its high performance until there was no ATP in the cell, that would be extremely dangerous to the muscle, because if we run out of ATP, we're going to go into that rigor state. And so if we're doing our exercise and then all of a sudden a muscle runs out of ATP, we are going to really damage that muscle, because it's going to lock down, those myosin heads are going to lock down onto the actin while we're still trying to do our exercise. So in a way, the fatigue is going to make sure that you slow down before you risk running out of ATP. So there's several factors that we're going to talk about. One is that if you have a lot of neural inputs saying to contract, meaning you're going to have lots of action potentials firing, you can get a buildup of potassium outside of the cell, because there's not enough time to get the gradients back to where they were at the beginning. And so if we have a lot of potassium outside of the cell, that means that the equilibrium potential for potassium will be less negative, which means that resting membrane potential will be less negative. But remember, the sodium and potassium channels need to get to that low, very negative membrane potential to be able to be either to become closed. And so if we don't allow that reset of the, for instance, sodium voltage-gated channels, they will remain in the inactivated state, and you won't be able to have another action potential. So the muscle cell will become less sensitive in a way to neural stimulation, because you've got this persistent depolarization of the fiber, which then prevents it from having another action potential until you get back down to those low resting membrane potentials that will cause the sodium channel to move from being in the inactivated state to the closed state, so it can be opened again. We can also have a buildup of all sorts of metabolites, which are going to affect different proteins or enzymes that are important in the process of contraction. One of those will be the sarcoplasmic reticulum calcium ATPase, or troponin and tropomyosin. And so if you impair those systems, then either you can't relax the muscle as quickly because your ATPase isn't as efficient as moving calcium back into the fiber, back into the sarcoplasmic reticulum, or if the troponin and tropomyosin system get less responsive to calcium, that will also prevent the muscle from quickly starting to contract. And then finally, we're going to talk about just how the buildup of inorganic phosphate, which is going to come off the myosin head during the cross-bridge cycle, if that builds up, that can slow the cross-bridge cycle, which again is going to lead to a reduced ability for the muscle cell to contract quickly. We're going to finish up talking about 3 different muscle fiber types that are going to differ in 2 different regards. One is in the type of myosin that they're expressing, whether it has an ATPase that is slow or fast. So a fast ATPase is going to be able to ratchet much more quickly, which means that the muscle cell will be able to shorten more rapidly versus the slow fiber. And then these fibers can also differ in the predominant metabolic pathway that they use to form ATP, whether it's glycolytic, meaning that it's going to tend to do more of the conversion of glucose to lactic acid without requiring oxygen, or it's going to be an oxidative fiber that is going to completely oxidize fuels like glucose and fatty acids to water and CO2, which we know is going to be able to provide energy for a very long time. So one fiber type are going to be slow oxidative fibers, meaning they have the slow ATPase, and they use primarily oxidative metabolism, which allows them to basically resist fatigue. An example of these sorts of muscle types would be muscles that we need for posture. They will tend to have more slow oxidative fibers. They need to be able to contract all day. They don't have to form a lot of force to keep us upright, but they need to be able to contract all day. And so that's what's shown here, where over 60 minutes, they're still able to produce the same amount of tension that they could at the beginning, and that will continue. Another fiber type are called fast oxidative glycolytic fibers, which can do oxidative or glycolytic metabolism, but they have the faster myosin ATPase, which means that they can contract more quickly. And since they're not completely devoted to oxidative metabolism, they do fatigue, but not that dramatically. So muscles for walking may have a fair number of fast oxidative glycolytic fibers, where you can walk at some speed for all day without fatiguing too much. So they have a kind of medium amount of ability to resist fatigue. And this is going to be in contrast to the fast glycolytic fibers that also have fast myosin ATPase, but they rely very heavily on glycolytic metabolism, which we said is going to last about 1.5 minutes. And so they can produce a lot of force quickly because it's a fast ATPase, and they tend to be larger in diameter. So that means that they can produce a lot of force because they've got more myofibrils, but they're going to fatigue more quickly. So and a good example of this would be muscles that you require for jumping. It requires a lot of force, but there is only a limited amount of time that you can jump without just falling to the floor, especially when you compare it to an activity like walking. So how do these fiber types come together in a muscle? It's important to remember that for the vast majority of muscles, all 3 fiber types are going to be present. It's a matter of the ratios of the 3 different types. Also remember, we've talked before about motor units, where we've got a single somatic motor neuron synapsing with at least several fibers. Those motor neurons are going to be synapsing with only one type of fiber. So each motor unit is going to have only one type of muscle fiber. So it may be a slow oxidative motor neuron that synapses only with slow oxidative fibers. And that's what's shown in this figure, where we've got motor unit 2 that's synapsing with fast glycolytic fibers that are large in diameter versus motor unit 1, which is synapsing with slow oxidative fibers that are small in diameter. And then we can also get into a motor unit and its size in terms of how many fibers it's innervating, whether it's going to perhaps be used for something like a finer movement versus a motor unit that's going to activate many fibers and maybe many large diameter fibers, which is going to produce more tension because you're just activating more myofibrils in parallel. So this gets into this idea of recruitment, of you're wanting to do a certain action, then very often the slow oxidative fibers in those muscles are going to be what are recruited first. They're going to start to contract. They're not going to produce tons of force because they're going to be fairly small in diameter, and they're going to produce force slowly because they're slowly cycling, but they can last for a long time. Then you'll tend to recruit fast oxidative glycolytic fibers if you still need more tension. And then if you require even more force to be produced, then you will also then recruit the fast glycolytic fibers. So we have two main ways that we can increase tension. We can send many action potentials to a certain number of fibers, which will cause them to produce maximal force, cause them basically to produce tetanus, force that's tetanus, or we can increase our number of motor units that are recruited so that many more fibers in the muscle are also contracting. So you can increase the number of fibers that are contracting, and you can increase how much force each fiber is producing, all based on which neurons are recruited and how often action potentials are firing. So let's just talk a little bit now. We've said we've got muscles that tend to have different fiber types. And we know that, for instance, if you do weight training, then you're going to increase the size of your muscles. And you're going to do that by causing hypertrophy of the muscle cells, which means causing them to get larger because they're adding more myofibrils. So that is going to allow them to produce more force so that you'll be able to lift more weights. So that's what weight training is going to do. Endurance training is not going to tend to increase the size of muscles. It's going to tend to increase their ability to use oxygen, because we know if you're doing an endurance sort of event that lasts a long time, you're going to be doing oxidative metabolism. And so you can increase the number of capillaries in the muscles, as well as the number of mitochondria in the oxidative fibers that allow those muscles to perform better longer. It's thought that training is going to change either the size of the fibers or the metabolic capability of the fiber, but not the number of fibers or the type of fibers. That you're probably born with a certain ratio of slow oxidative fibers versus fast glycolytic fibers, and that's not going to be very changeable. But what you can do is either make your fast glycolytic fibers larger or increase the capability of the slow oxidative fibers to use oxygen so that you can train and improve at a certain activity by doing that activity. So we've talked about how we can have isotonic contraction where we form a certain amount, a constant amount of tension that will shorten the muscle, or we can have isometric contraction where we keep the tension equal to the load so that the muscle does not shorten, and that we're going to have maximal velocity when we have zero load, and that we can sum contractions because our twitch, our action potential is so short in relationship to the duration of the twitch, and that speed of contraction is going to be determined by whether we have slow or fast myosin ATPase. And then we're going to use ATP for contraction, and it can be generated by creatine phosphate, donation of phosphate, or under aerobic or anaerobic conditions, and that if we need to resist fatigue, then we're going to use aerobic metabolism.